Welcome to the Architecture and Analysis module in the Mobile Application Security Foundation series brought to you by NowSecure. The objectives for this course are to examine the fundamentals of Android and iOS architectures and provide insight into how each layer in the stack works together. Finally, you will learn about the important concept of sandboxing and the role it plays in securing these platforms. In this course, we'll cover Android and iOS architecture fundamentals, the mobile attack surface, and dynamic and static analysis. Let's get started. Android and iOS Architecture Fundamentals module. In this module, you will learn key features and utility of platform architectures along with frameworks and system components. We will also discuss Android and iOS sandboxing and how it's used to secure the platforms. Android is an open source software stack based on Linux that can run on a wide range of devices and configurations. The Android software stack contains a Linux kernel, which is a collection of C or C++ libraries that are exposed through application framework services, runtime, and application. Android apps do not have direct access to hardware resources, and each app runs in its own virtual machine or sandbox. This enables the operating system to have precise control over resources and memory access on the device. Android comes with a set of core apps for email, SMS messaging, calendars, internet browsing, contacts, and more. The system apps function as both apps for users and provide key capabilities that developers can access from their app. For example, if your app would like to deliver an SMS message, you don't need to build that functionality yourself. You can instead invoke the previously installed SMS app to deliver a message to the recipient you specify. The entire feature set of the Android operating system is available to you through APIs written in the Java language. These APIs form the building blocks you need to create Android apps by simplifying the reuse of core system components, modular system components, and services. Many of the core Android system components and services, such as ART and HAL, are built from native code that requires native libraries written in C and C++. The Android platform provides Java framework APIs to expose the functionality of some of these native libraries to apps. For devices running Android version 5.0 or higher, each app runs in an isolated process and with its own instance of the Android runtime, or ART. ART runs multiple virtual machines on low-memory devices by executing DEX files. DEX is a bytecode format specifically designed for Android that's optimized for minimal memory footprint. The Android runtime is the engine that drives our apps and libraries, as well as the foundation for the application framework. The hardware abstraction layer, or HAL, provides standard interfaces that expose device hardware capabilities to the higher-level Java API framework. The HAL consists of multiple library modules, each of which implements an interface for a specific type of hardware component, such as the camera or Bluetooth module. When a framework API makes a call to access device hardware, the Android system loads the library module for that hardware component. The foundation of the Android platform is the Linux kernel. Android runtime relies on the Linux kernel for underlying functionalities such as threading and low-level memory management. Using a Linux kernel allows Android to take advantage of key security features and allows device manufacturers to develop hardware drivers for a well-known kernel. The Android platform uses the Linux user-based permissions model to isolate application resources. This process is called application sandboxing. The goal of sandboxing is to separate app data and code execution from other apps on the device. This separation adds the first layer of defense. Each application is assigned a user ID or UID, which is inherited from the underlying Linux operating system. This is done dynamically on installation and essentially establishes the identity of the application. At a basic level, the application can interact with any file owned by its UID, but not any others unless permissions are shared with another application or the operating system. The user is also the owner of the application directory. This UID separation forms the foundation of the application sandbox and prevents anything other than the app itself, certain components of Android operating system, or the root user from accessing its data. Apple defines the collection of mechanisms and technologies as a sequence of layers inside the operating system. Each one of these layers comprises multiple frameworks to be used and implemented through your application. At the uppermost level, iOS works as an intermediary between the underlying hardware and the application. Apps do not communicate to the underlying hardware directly and are isolated from each other via Apple's iOS sandbox, which is a mandatory access control mechanism that controls the resources an app can and cannot access. Compared to Android, iOS offers very few inter-process communication options, minimizing the potential attack surface. Touch is also known as the application layer. It acts as an interface for the user to work with the iOS operating system, supporting touch and motion events and many more features. The frameworks in this layer include the EventKit framework, which displays the calendar and reminders to the user and provides controllers for viewing and editing calendars and reminder information, the GameKit framework, which provides support for users to share their game-related data online using the Game Center, the MapKit framework, which allows developers to incorporate fully functional and customizable maps in any application, and the PushKit framework, which provides specialized notifications related to the app's complications, file providers, or VoIP services. The media layer holds the frameworks that enable all the graphics, audio, and video technologies of the system. Some frameworks include UIKit Graphics, which provides classes and protocols that help configure your drawing environment and render your content. Core Animation, which is a framework that optimizes the animation experience of apps in iOS. The Media Player framework, which controls playback of the user's media from an application. And the AV Kit, which implements various easy-to-use interfaces for video presentation, recording, and playback of audio and video. The core services layer holds many important frameworks necessary for making a mobile phone a smartphone. Some frameworks for core services include the Address Book framework that provides access to the contact details for the user, the CloudKit framework, which provides a medium for moving data between your app and iCloud, the Core Data framework, which is used to save your application's permanent data for offline use and to cache temporary data, the Core Foundation framework, which gives fundamental data management and service features for iOS apps, and the Core Location framework that gives the location and heading information to apps. The Core OS layer holds the low-level features that most other technologies are built upon. Notably, this layer provides support for 64-bit app development and enables applications to run faster. The Accelerate framework provides hardware-optimized C-based APIs for performing complex and large number math, vector, digital signal processing, and image processing tasks and calculations. Its most common use is in gaming apps. The External Accessory framework provides the ability to communicate with external accessories connected physically to the iPhone via the 30-pin dock connector or wirelessly via Bluetooth. The Security Services framework provides all the security interfaces you would expect to find on a device that can connect to external networks, including certificates, public and private keys, trust policies, keychains, encryption, digests, and hash-based message authentication code. The Local Authentication framework provides capabilities for requesting a passphrase or Touch ID authentication from users. The iOS sandboxing process is very similar to that of the Android sandbox. All third-party apps are sandboxed, so they are restricted from accessing files stored by other apps or from making changes to the device. Sandboxing is designed to prevent apps from gathering or modifying information stored by other apps. Each app has a unique home directory for its files, which is randomly assigned when the app is installed. If a third-party app needs to access information other than its own, it does so only by using services explicitly provided by iOS. Furthermore, system files and resources are also shielded from the user's apps. Most iOS system files and resources run as the non-privileged user mobile, as do all third-party apps. The entire operating system partition is also mounted as read-only. Unnecessary tools such as remote login services aren't included in the system software, and APIs don't allow apps to escalate their own privileges to modify other apps or iOS. Android and iOS have complex architectures that the analyst must understand in order to effectively assess and secure a mobile application. Mobile Attack Surface Module. In this module, you will learn about the layers of the mobile attack surface, components within those layers, including states of data storage where misconfigurations may exist, along with back-end testing. The primary layers of the mobile attack surface are the technology stack, communication protocols, and the greater mobile ecosystem. A series of networks and interconnected systems exist to support modern mobile devices. The abilities of mobile devices are greatly enhanced by software applications and their supporting cloud services. Mobile operating systems provide dedicated application stores for end users that offer a convenient means of adding functionality. Application stores can also create additional threat vectors for attackers to distribute malware or other harmful software to end users. This is especially true of third-party application stores not being directly supervised by mobile OS vendors. Mobile applications may traverse many networks and interact with systems owned and operated by many parties to accomplish their intended goals. Here we can see at a high level components of the mobile attack surface: app code or code functionality, data at rest, data in motion, and the API backend. Let's define these components and learn some examples of potential attack vectors that misconfigurations or poor development practices may enable. Ideally, security should be considered throughout all phases of development. In reality, however, security is often only considered during the late stages in the software development lifecycle. If used properly, MASVS controls, which were outlined in a previous module, can help ensure proper development best practices and can guide a developer to proper implementation of adequate security controls. Some examples of poor development practices that may expose attack vectors include improper use or identification of third-party libraries and not assessing these libraries for vulnerabilities, use of debugging code and developer assistance code in production builds that may expose backdoors or hidden settings, and failing to ensure the app is signed and provisioned with a valid certificate of which the private key is properly protected. Data at rest is data that is not actively transmitted from device to device or network to network. Simply put, it's data that is stored on the mobile device. When attempting to access this data, an adversary gaining physical access to the device is the most likely scenario. In that case, additional protections can be implemented to make retrieving sensitive data more difficult. Some examples of misconfigurations that may expose or leak potentially sensitive data include improper or lack of use of system credential storage facilities to store sensitive data such as PII, user credentials, or cryptographic keys, use of deprecated encryption methods and cryptographic algorithms, sensitive data stored locally on the device that should instead be retrieved from an endpoint when needed and only stored in memory, and improper use of IPC mechanisms that may cause exposure of data, especially sensitive data. Data in motion is data that is actively moving from one location to another. This can be across the internet, within a private network, or from one device to another. As your data moves across the internet or a private network, it passes through several servers, exchanging information before it reaches its destination. This allows opportunities for malicious actors to access your data. Ensuring the confidentiality and integrity of information exchanged between the mobile app and remote service endpoints is essential. Here are some examples of potential data exposure if security controls are not properly implemented. Transmission of data in clear text that may allow the data to be intercepted through man-in-the-middle attacks, outdated connectivity and security libraries, such as using a deprecated version of TLS or transport layer security, and use of a certificate store other than that which belongs to the application, or improper certificate pinning. This allows the app to establish connections with endpoints that offer a different certificate or key, even if signed by a trusted certificate authority. Back-end testing is a testing method that checks the server-side or database used by the applications. The purpose of back-end testing is to gain an understanding of the security posture of these endpoints. Ensuring the security of endpoints is essential for protecting the information that is both at rest and in motion from the back-end to the device. Some examples of testing and scanning that take place during these assessments includes operating system detection. Knowledge of the operating system will allow analysts or attackers to gain an understanding of what vulnerabilities may be present in the version of the OS that is in use. Service discovery. It is common for these endpoints to have various services exposed to the internet for a variety of uses. This scan details these services and their versions. With this knowledge, the analyst can assess if the exposed endpoints are necessary and running on current versions. And network mapping. By observing the network layout, the analyst will gain a deeper understanding of the function of different pieces of the network, along with potentially vulnerable systems and attack vectors. The mobile ecosystem provides many potential vectors of attack. Ensuring security controls are properly implemented in all stages of development and throughout the ecosystem is integral to ensuring confidentiality, integrity, and availability of systems and information. The Dynamic and Static Analysis module. In this module, you will learn about dynamic and static analysis and their roles in mobile application testing. The process of dynamic and static analysis is integral throughout the application testing process. They allow analysts to discover misconfigurations and vulnerabilities, or to validate that the application is following best practices for its use case. Static analysis is a test of the internal structure of the application rather than functional testing. Dynamic analysis adopts the opposite approach and is executed while a program is in operation. Static application security testing, or static analysis, involves examining an application's components without executing them by analyzing the source code either manually or automatically. In most cases, a hybrid automatic and manual approach is used. During static analysis, the mobile app's source code is reviewed to ensure appropriate implementation of security controls. Automatic scans catch the low-hanging fruit, and the analyst can explore the codebase with specific usage contexts in mind. Manual code review is a form of static analysis and requires an expert code reviewer who is proficient in both the language and the frameworks used for the mobile application. A full code review can be a slow, tedious, time-consuming process for the reviewer, especially given large codebases with many dependencies. Dynamic application security testing, or dynamic analysis, involves examining the mobile application during runtime. This type of analysis can be manual or automatic. It usually doesn't produce the information that static analysis provides, but it is a good way to detect interesting elements like assets, features, entry points, etc. from a user's point of view. Dynamic analysis is generally used to check for security mechanisms that provide sufficient protection against the most prevalent types of attack, such as disclosure of data in transit, authentication and authorization issues, and server configuration errors. Dynamic analysis is conducted both at the mobile platform layer and against the backend services and APIs where the mobile app's requests and response patterns can be analyzed. Effective analysis of mobile applications must be done using both static and dynamic methods of analysis in order to gain a comprehensive understanding of configurations, misconfigurations, and vulnerabilities that may exist in the application.